In this video, we're going to take a closer look at what is really happening when an ionic compound dissolves in water. So in the most general sense, we can say that we have an assortment of bonds and intermolecular forces that are breaking and forming throughout this process. But we want to take a look at exactly what those are. So what is breaking, what is forming, what is going on here? So essentially there are three main things that need to happen in order for something to dissolve. The first is the one that we've essentially already talked about, is that our ionic bonds need to break. So the ionic bonds in the solute break. So we've discussed in previous videos that when ionic compounds dissolve, they break apart into separate ions. And we've seen a bunch of examples of this. We've used this to write ionic equations. So this process of splitting apart is often referred to as either ionization or dissociation. In this context, those are the same thing. That we are splitting apart into two separate ions, so it is ionizing or dissociating. So, for example, when sodium chloride dissolves, we know that what we get is aqueous sodium ions and chloride ions. So if we think about what that means at the molecular level, if we have a sodium ion and a chloride ion, in the solid state, these are connected by an ionic bond. So in order for those things to separate, when this thing dissolves, we end up with that sodium ion and that chloride ion no longer attached to one another. This means that that ionic bond has been broken in the process of dissolving. So when compounds dissociate, we're breaking all of the ionic bonds in there. So the next thing that has to happen in order for something to dissolve in water is that some of the hydrogen bonds between the water molecules, not even close to all of them, just a few, will also break. So again, just a few, not all of them. This needs to happen essentially to make space for those ions, that the ions are dissolving into the water. The water is mostly all hydrogen bonded with other water molecules, so they're kind of connected in their own way, and the ions need to insert themselves in between. So in order to do that, they're probably going to disrupt some hydrogen bonds in the process. So this needs to happen in order to make room for the ions. Make space for ions. So a quick reminder about hydrogen bonding and how all of that works is that hydrogen bonding is an intermolecular force. Which means that it occurs between two separate molecules. So you have two water molecules. They are attracted to one another via hydrogen bonding. So it is important to remember that this is much, much, much weaker than a covalent or an ionic bond. Hydrogen bonds are not really technically bonds. They are an intermolecular force, so the name confuses everyone all the time. So if we wanted to represent hydrogen bonding, if we look at a water molecule, H2O, move this a little bit. So if we have a water molecule, H2O here, and another water molecule, these two water molecules can form a hydrogen bond in between them, but it is important to note that this is different than a regular bond. So you should never ever indicate that these two things are connected by a solid line. A solid line means a covalent bond, which is not what we're showing here. So if this is one water molecule over here, this is a separate water molecule, and they are attracted to one another through hydrogen bonding. And it's always highly polar molecules that undergo hydrogen bonding or participate in hydrogen bonding, and it's the oppositely charged ends. So the hydrogen from one end of our molecule is attracted to the oxygen of the other. The hydrogen end of water molecules has a little bit of a positive charge on it, and the oxygen end has a little bit of a negative charge. So this is the basis for the hydrogen bond, that opposites attract. Opposites attract is so central to so much of chemistry, but recognizing that this positive thing is going to be attracted to this negative thing, and that's all a hydrogen bond really is this attraction between two different particles of opposite charges. So some of these are going to get disrupted, and the ions, as they dissolve, will kind of insert themselves in the middle in between different water molecules. And when they do that is when our third thing happens, which is that a new intermolecular force forms, known as an ion-dipole force. Or an ion-dipole interaction, whatever you want to call it. So this is an attraction between the ions that are dissolved. So those are our solute ions. And a polar solvent. In this case, we're talking specifically about water. And once again, opposites attract. So any cations will attract the negatively charged end. So remember that cations are positive. The cat has paws. Cations will attract the negative end of the water molecules. So continuing to use sodium chloride as an example, if we have our sodium cation after it has dissolved, the negative end of a water molecule is the oxygen. So if you were able to zoom in and look specifically at one of the sodium ions dissolved in solution, you would find that the water molecules around it have oriented themselves so that the negative end is pointing towards that positive ion. And this interaction in here between the ion and the water molecules is our ion-dipole force. Because this oxygen in each one of our water molecules has a slight negative charge, the hydrogen is where the positive charge lies in a water molecule. Similarly, but opposite, anions will attract the positive end of the water molecules. So if chloride is our anion from our previous example, you would find that the water molecules around a dissolved chloride ion have oriented themselves so that one or both of their hydrogen atoms is pointing inward. And our ion-dipole interactions are going to be between that chloride ion and the water molecules. Because these hydrogen atoms all have a slight positive charge on them that is attracted to the negatively charged chloride ion. So if we put all of these ideas together, we can get a pretty comprehensive picture of what a solution really looks like at the molecular level. So before our solute dissolves, so we have our solid solute down here, all of our ions are connected by ionic bonds. So we have ionic bonding, ionic bonds in our solute. Are what's holding that solute together. And then in our solvent, so this is all water, there would be lots and lots and lots of water molecules, but they are attracted to one another via hydrogen bonds. So between oppositely charged ends of separate water molecules, we have hydrogen bonds between solvent molecules. So when our solute dissolves, we know that it's going to break apart. So all of these ions are going to end up separated all over our solution. So we come over here, we can represent that as we have before. Where everything is just randomly scattered throughout the solution. But the important part here is that all of our ions are completely separated, that none of them are attached to one another anymore, because this is dissolving completely. So just to keep everything straight, label our charges. As positive and negative. Because if we take a look at our solvent molecules, at our water molecules, we're going to find that many of them have oriented themselves around these dissolved ions in such a way that the negative end of the water molecules is oriented towards cations, and the positive end is oriented towards the anions, forming the ion-dipole forces like we discussed. I'm only going to draw in a few examples because otherwise this diagram will just get too cluttered. But I can show a few. So around our cations, we would have water oriented with the oxygen facing towards that positive charge, since the oxygen end is negative. And this would be the case around all of our cations. Just going to illustrate this one to avoid too much crowding. So these are our ion-dipole interactions. Around anions, we would have the same idea, but in the opposite direction, where now the hydrogens, which are positively charged, point in, attracted to that negative anion. And our ion-dipole interactions would be between that anion and those water molecules in here. And we do still also have hydrogen bonding between water molecules. So we disrupt some of it to make space for these dissolved ions, but we would also still have plenty of hydrogen bonding existing just as it normally would between the many water molecules that are present still and not around dissolved ions. So this gives us a pretty good idea of what's going on when the solute and solvent are connected solute and solvent are still separate before anything has dissolved versus what does it look like afterwards.